So the next example is going to utilize these control volume analyses to evaluate the thrust on a propeller. So here we have an example of a propeller shown here. See the propeller blades, it spins or rotates around this axis at a rate of omega. Has a radius r, it produces a thrust to the left, and it's moving into a velocity, an oncoming velocity, which is going to the right at a velocity of v naught. So in evaluating this, one of the key things we need to do is understand momentum theorem and how we would arrive to forces on the body. This term is rate of change of momentum in a control volume. Doesn't directly give us thrust. This one is mass flux out of the control volume, not really going to give us force. These two terms, when evaluated directly on the blades themselves, give us these specific terms. So what we're going to do is identify what these two terms are and understand how it changes with respect to the momentum in the control volume or in the surrounding areas. Okay, so the first thing to do is, for this one, we're going to write down a few assumptions. So let's assume one steady flow. This thing's rotating at a steady rate. Things aren't varying in time. Incompressible. We're going to make a few other comments. Constant loading on the propeller, which implies uniform flow in wake propeller. And we're going to end up putting a control volume where P approaches P infinity on control surfaces and tau on the fluid approaches 0. So this implies R from geometry. Okay, so we really don't have our control volume yet. And what we do with the propeller is a little bit different. So the idea of a propeller is you draw a propeller disc, give it about an axis, has a radius r, but we want to treat it as essentially everything inside of there. This could represent the blade, but each individual blades, but let's just treat it as things are moving so fast. Let's look at it from a mean sense in that region of interest. Then we're going to focus on two key components. So this propeller is going to have a streamline on the outside. It's going to look like, for a propeller, it generally grows and shrinks on either side. I mean, just from a quick explanation, you can think of the difference between if any of you have used a leaf blower versus a vacuum. The leaf blower blows very hard, but it doesn't suck that hard. Same kind of thing happens with a propeller. And we're going to evaluate it in two different points. So we're going to draw our control volume, exit of the control volume, and an entrance right here. What we're going to do is extend it beyond. And about this axis, this extension point is going to be, I'm going to call it R naught. If we evaluate the velocity at various points in this, the velocity on the left side. Well, let's first name the surfaces. So this is going to be the inlet, which is surface 1. Then we have what's going on the sides, which is surface 2. Then the primarily outflow, which is going to be surface 3. We also want to have our surface that confines the body, which is going to be surface 4. So when we look at this, what's going on with respect to what we know? Remember, it's moving. So on this entire surface, we have V naught, we're calling it this time. And it's also going to have P infinity. On this outflow, what we're going to assume, actually, it's not V naught. It's V1. I'm going to change it here, and I'm going to change it here so it's consistent with my notes. So in the outflow, inside of this, so this is far, so everything is uniform all the way on this left surface. That is V1. Everything on, so on this surface, side of the streamline, it's going to be V1, V1. But what we're going to do is inside this streamline, this propeller, it pushed this fluid to go faster, and we're going to call it an accelerated velocity V2. Okay. So remember, this is a stream tube. Passes through the propeller. Out here, this entire boundary is going to be far, so the pressure here is going to be P infinity. And now let's go on parts 2. On body 2, pressure is going to be P infinity. And we're going to have a velocity V naught. However, our stream tube is going to be defined by this line. And this line enables some slight component, negligible from a momentum perspective, not negligible from a mass perspective, that passes through that line. So this, unlike what we did with an airfoil, this is not a streamline. Our stream tube is used for this analysis. But this one we avoided. So this is our new control volume, our control volume approach for this propeller. So what we need to do, again, is utilize this. So what it means is we have to know the entire mass flux out of the system. We have a mass flux into the system on the left side, out on the right side, and then through surface 2, we have another mass flux that we can't really account for, given the inputs that we know. This demands us to use conservation of mass. Obtain momentum flux into surface 2. Okay. So conservation of mass says that the mass flux in the system plus the mass flux out of the system equals 0. Wait, no, the mass flux, the mass in the system changes in time with respect to the mass flux out of the system. This is steady, so that is 0. And this term we're going to break into 4 different terms. So we have surface 1, surface 2, surface 3, and surface 4. So, what was surface 1? Recall that it is the mass flux into the system. So the mass flux into the system. So here, V equals V1I, gas equals negative DSI, because remember, ds is pointed in the negative direction. When we bring that down, we end up with a density times V1. Oh wait, before we bring that down, when we take V dot ds, we end up with negative V1 ds. So now when we bring that down, density is constant. V1 is constant on that surface. Take over this negative sign. Up with this. This term ends up being R naught times pi R naught squared. Our area. Remember, we have this area. We have a cylindrical tube controlled volume with a radius of R naught. So we go, then next thing we do is we go to the second term, this one. So here, yes is this, but in general, we don't know what's going on. This is actually what we're after. So we're just going to call it mass dot so m dot 2. The next one is this third term. How do we evaluate that? Here our ds is out and our velocity is out. So V equals, and for the time being, I'm just going to say so for the time being, I'm just going to say V is in the I direction, S is in the I direction, hence E dot ds equals V ds. V dot ds equals V ds. It's all in the I direction. And when we go through and evaluate this integral, it's a little more complicated. The other thing we have to evaluate when we evaluate this is what is, I didn't write this out, but this has already a radius R2. We're just going to call it R2. So when we evaluate this integral, we're going to end up with 2 integrals. One, well, it's most easily evaluated with 2 integrals. The first one is what's going on, what's the momentum flux through here, which is going to be rho V2 pi R2 squared plus what's going on outside, which is V1 pi R naught squared minus R2 squared. Rho. So this ends up being this integral. This first term is in wake, or we're in wake stream tube outside of wake stream tube. Okay, this term, this is the term on the body itself, on the actually operating on the blades, and very similar, and that is going to be 0. There's no flux through the blades, hence that goes to 0. Then we end up with 0. Set that equal to 0. And what we want to do is solve for m dot 2. So m dot 2 is going to equal this term, rho v1 pi r naught squared, minus these two terms, minus rho v2 pi r2 squared, minus rho v1 pi squared. Minus r2 squared. What we can do is simplify. One thing you might see is that this term and this term equate. So that goes to 0. This term and this term are in addition. So we actually double that. So we end up with actually, they are not in addition. We end up with rho pi times r2 squared times v1, so a negative, wait, no, a negative and a negative, so it's positive here, minus v2. Hence, the mass flux entrained through these two surfaces all the way around this cylinder is exactly is described based on this. Okay, now that we have that, we're able to obtain the momentum flux through that boundary. So now we go to conservation of momentum, which yields thrust. Okay. Similar to before, we look at the range of momentum in the control volume plus the momentum flux out of the control volume equals to the pressure acting on the control volume and the wall shear acting on the fluid at the control volume surfaces. Similar to before, that is 0. We're steady. This, then we're going to break this up to a left-hand side and a right-hand side. Okay, so for our left-hand side, what we want to do is break this term up into 4 terms. 1, surface 2, surface 3, and surface 4. Surface 1, just like before, this term is identical. V dot ds equals negative vs, negative v1 ds. So one difference is, so this one, that equals v1I. This equals v1 ds. So what we end up with is rho v1 squared times integral of ds v pi r naught squared. The second term, remember this is the control surface on the outer periphery. This is probably the trickiest part. What is rho v dot ds? M dot, we can do is rewrite this integral into, well, let's just write a few things out here. This term is v1I, then rho v dot ds. That's the term that we don't know. But that actually ends up being what this m dot 2 term was. So we can actually write this entire term as m dot 2 v1. Just speaking of this, I forgot to carry this I through over here. So don't forget this I. So this entire term ends up being rho v1 squared pi r naught squared I. This entire term, if we plug in what we got from before, it is going to be rho pi little r squared times v1 minus v2 times this one, v1I. This term here is going to be probably the most complex of these terms. Just like before, this term is going to be identical to what it was before. And if we write this out, it's going to be, hold on. It's going to be rho times v2 pi r squared 2 plus, this is squared, v naught squared pi naught squared minus r2 squared. So this one is the flux, the momentum flux through here. And the other one is the momentum flux out here. The second term is a momentum flux on the outer periphery. So that term ends up being rho V2 squared R2 squared plus V naught squared pi R naught squared minus R2 squared. Last one, that one equals 0. So this is the general equation that we end up with when we evaluate the left-hand side. Now let's move to the right-hand side, which again has these pressure and shear force terms. So because we put everything because we pushed everything out, all our boundaries are as far as we can make them from the repeller, the pressure equilibrated to P infinity. If we would have tried to apply this at the stream tube itself, that would not necessarily work. But because we are, it does work. So when we look at this, we want to evaluate this on surfaces 1 through 3. Separately from surfaces 4. And the same for the shear on the fluid. This is 1 through 3. And surface 4. Since P is constant on all these surfaces, the sum becomes 0. And because this is far and there are no shear forces, that approaches 0. Then we're left with what is going to be the force, the prop on the fluid, which is going to be negative pressure ds plus F ds. So these are the reaction force of the propeller acting on the fluid. So if we want thrust, we just take the negative value of that. And we do not actually have to evaluate any of these. It's exactly what we're after. So if we combine the left and right-hand side, we end up with an equation that says, let's see, rho V1 squared pi R naught squared in the I direction. You know, coming back up here, I realized that term gives us an I direction. I didn't keep track of that. Then we have this term plus rho pi R2 squared minus V2 V1 I. And this term plus rho on 2 squared pi R2 squared plus V naught squared pi R naught squared minus R2 squared equals negative thrust. So what we can do is start eliminating terms. If we look closely, we see, oh, I see one other issue. This is not V naught, that is V1, and this is V1. So if we come back here, what we can see is that we can start eliminating several terms. So so remember that this was a negative, and that's a negative because it's momentum flux in. One of the nice things about going through this is if you see any errors in your signs or vectors, it'll all come up. So keep that in mind. So if we evaluate this term is also going to be canceled out by, if I'm not mistaken, this term. Nope, not that term. It's rho v1 squared pi r naught squared. And this term. So we could cancel that term out with this term. This particular term is going to equate with and r squared. Here we have a v1 squared, a v1 squared. So we use another color. This term and this term cancel out. So then we end up being left with negative thrust equals rho pi r2 squared, negative sign v2 v1 in the I direction, plus rho v2 squared pi r2 squared in the I direction. Let me check that with my notes. Yes. What it ends up coming down to is that thrust can be described as rho times pi r2 squared times v2 minus v1 times v2 in the I direction. And that's negative thrust. So here we have an equation that relates thrust to the thrust from the propeller to the what's going on at various points in the flow. So key things. This is the slipstream wake, right? The size of the slipstream. So we have remember, we have a propeller here with a radius r. This is the radius in the wake. V1 is a free stream velocity, and V2 is the velocity in the wake. Again, within this stream tube that passes through the propeller. Okay. So, one other comment about this. Right here, we have this negative thrust sign. Why is it negative? So if it were a positive thrust, so positive thrust is in this direction, but when we talk about thrust, we really want to think about it operating in the negative direction. So if we convert it to understanding in the negative direction, it will, so when it's written as this negative with a negative sign, it basically says, so thrust is in the positive direction. So written with this negative sign, it implies that this relationship has a thrust moving to the left. So keep that in mind. Okay. So there we have applied conservation of momentum, but we could still gain a little bit more insight of this, the context of this. And what we're going to do is employ the conservation of energy, specifically this 1D quasi 1D energy equation. And what it enables us to do is understand the detail of velocity through the rotor. So what happens here? You can look at this from this inflow plane. Let me just draw this one more way. So this is our rotor wake, or this is our rotor with a velocity r. Then we have this, I'm not drawing this all that well. Then we have this rotor wake, where this has a velocity of r2, and we'll just call this r1. If we evaluate the energy through the system using this quasi 1D energy equation, what we can look at is the value of P plus 1/2 rho V squared. And what we're going to see is everywhere to the left of the rotor, it's going to be constant, just like what Bernoulli equation says. Then the rotor puts a head rise into the system, and it's going to be constant thereafter. So this is going to be the head rise from the propeller. So here we're going to, and this head rise is going to correspond to a delta P given by PR and PL. So we'll call it PR minus PL. Delta P also is going to equal density times the head rise associated with a pump. So using this, we can also estimate another way to evaluate torque or thrust. Thrust is also approximately equal to the area of the disk times that pressure rise. You could say that this also equals to the area of the disk times the head rise associated with this. propeller. So what we can do is apply this quasi-1D energy equation. And what it basically says is, remember, this is point 1, this is point 3. I'm going to call this L, and this is R. And we could write this quasi-1D energy equation as follows. P naught plus 1/2, not P naught, P1 plus 1/2, actually I shouldn't even call it P1, P infinity plus 1/2 rho V1 squared plus delta P equals the pressure on the left plus 1/2 rho the velocity at the left squared plus delta P, which is also going to equal the pressure on the right side of the rotor disc plus rho VR squared, also equals restraint pressure plus 1/2 rho. So anytime you're on the left, anytime you're to the left side of this, you add this delta P. When you're to the right, that head rise is already added to the system, so it's not really needed. So what we could do is invert these equations, because we have all the knowns, to obtain delta P, which equals, from this equation, we know delta P is about equal to thrust on pi r squared. And from this in this equation, delta P equals 1/2 rho V2 squared minus V1 squared. So what we can do is obtain a relationship for, so what we want to do is tie this back to thrust. So thrust equals so what we could do is write thrust as pi r squared on 2. We could expand this and rewrite this as this term as V2 minus V1 and V2 plus V1. So the next thing we want to do is obtain a So the next thing we could do is equate this to our previous equation for thrust, given here. So it's going to equal to rho V2 pi R2 squared V2 minus V1. And here we're going to get rid of the sign. I mean the vector, because this is a scalar quantity. And we're also going to consider this in terms of thrust acting in the direction that we're writing everything. So for that reason, we consider we'd get rid of this sign. So when we compare these two equations, what we could see is that this term and this term cancel, pi cancels, and we end up with V2 plus V1 on 2 is equal to rho V2 R2 squared on R squared. So what we want to do is we reduce this. And the way we reduce this is coming back to this scenario and apply conservation of mass. Here we know that the mass going through this system has some velocity. I'm going to call it velocity at disk. And this one has a velocity too. So conservation of mass says rho velocity of disk times pi r squared equals rho velocity 2 pi r2 squared. What we can see is it compares to this equation. All we have to do is divide through by r squared. And divide out pi. And we could rewrite this equation as rho divides out as well. We could rewrite this equation as v disk. So what that says is that the velocity at the disk, so that is the velocity here, is going to equal velocity upstream plus the velocity in the wake on 2, or the mean velocity. So another way to think about propellers is in the context of what it does at the disk. So the velocity at the disk, we could also write this as the velocity of the free stream plus an induced velocity. So this induced velocity would be described exactly as where W is described as the V disk minus V1, or from this equation, it is V1 plus V2 on 2 minus V1 . And in general, you could describe these disk velocities in terms of that. So again, induced velocity W is the velocity that the propeller induces disk when thrust is generated. When you write things in terms of induced velocity, you could write that thrust is given exactly as rho times pi r squared. So velocity at the disk, or V1 plus W times 2W. What this implies is that thrust is directly proportional to the induced velocity at the rotor disk. And lastly, you could also write this in terms of power. Power is given as, this is called an induced power, which is given as thrust, force, times the velocity it's generated at, or V1, or the velocity at the disk, or V1 plus W. So these are a few key concepts in the context of a propulsor or propeller that are readily available or evaluated using conservation laws. And I think it shows a lot of different ways that conservation laws can be used.